Greetings everyone, welcome back to Calc 1 again, and here's one of my favorite topics, L'Hopital's rule. I know it looks like hospital, everybody says L'Hopital's rule, it's L'Hopital, it's French, okay? We need to talk about this one because this is a very important result where derivatives actually turn back around and help us with limits. Right? We use limits to define derivatives, and we're going to loop back around now and have derivatives help us with some more difficult limits. Okay, so the idea is this. If you have a limit, any old limit, and when you perform the substitution, you get a 0 over 0 or infinity over infinity. By the way, the infinities can be negative or positive. You can have negative infinity over positive infinity, so on and so on. What you can't have, you cannot have 0 over infinity or infinity over 0 or infinity over a number or, things like that. It needs to be an indeterminate form when you try the substitution on the limit, because you always start by plugging the numbers in a limit just to see if it works. Okay, so if it's one of those specifically, then L'Hopital's rule says that the limit that you're trying to do with f of x over g of x, okay, is equal to the same limit value, right? Notice the a is the same, but then you do f prime over g prime. Very important. Notice this is not a quotient rule. Do not do the quotient rule. It's literally the derivative of the top, the derivative of the bottom, straight across. Okay? Now what I have here is not by any means a full proof, but just so that you can get an idea of where this rule is coming from. Imagine that you have f of x, the limit as x approaches a of f of x, and the function value itself equal to 0. Remember what that means is it's continuous at a, and the function value and the limit are both 0. And then the same thing for g. And we're also going to assume that since it's continuous, that it's also differentiable there. We're not talking about any crazy cusps or anything like that. Okay? Then the limit as x approaches a of f over g is equal to, and then notice all I did was subtract 0, right? You can subtract 0 from anything. It doesn't do anything, right? Yeah. But we already said that f of a was equal to 0, right? And g of a was equal to 0. So I can actually do f of x minus f of a over g of x minus g of a. That should sort of start looking a little familiar there. If I divide both top and bottom by x minus a, it should look very familiar. If you look, the limit as x approaches a of f of x minus f of a over x minus a, that's the derivative of f at point A. Same thing down here, derivative of g, but that uses up the limit. So what we have so far is that the limit is equal to the derivative value of f over the derivative value of g. But of course, if we assume that the derivative itself is continuous, not just the original function, but the derivative function also being continuous, then the limit value of the functions should also be equal to the function values. So basically it's just two different ways of writing the same thing. Again, this isn't a full proof, okay? But you can see where some of the idea of this is coming from. It's just a slight algebraic manipulation with limits, and derivatives are already involved with limits, okay? That was just for the 0 over 0 case though. To argue for the infinity over infinity case, you need a bit more of an advanced argument. And you can sort of see why it would work, because you can take a 0 over 0 limit, and if you take the reciprocal of the numerator and denominator pieces, you'll notice you'll get the infinity over infinity, or vice versa. You can take an infinity over infinity and do a reciprocal and get a 0 over 0 set up. Okay? So the two cases are actually linked, and that's why those are the only two indeterminate forms that you actually can use with this, because technically it ends up being the same setup, just two different ways of looking at it. Okay? So here's the basic idea, right? You get a limit that has some sort of numerator and denominator in it, or all numerator with some negative exponents or whatever. Find some way to set your limit up in a fraction like this. If you get one of these two indeterminate forms, then we straight up just take the derivative of the top and the bottom separately, and then we try again. That's what L'Hopital's rule does for us. Okay, so some examples. Right here, we would have done limits like this a long time ago already, and this is one of those ones where I'm getting 0 over 0. Notice if I plug in -5, right, I get 0 in the bottom immediately. And -5 cubed is -125, so I'm getting 0 in the top also. Before, what that would tell you is, hey, you can probably algebraically manipulate this sum. So back in the first chapter, we would have worked this limit like this. We would have said this is equal to the limit as x approaches -5 of x plus 5 times x squared plus 5x, minus 5x actually, plus 25, right? And the denominator of x plus 5, all I did was factor, right? All I did was do the sum of two cubes factoring method, and then that allows us to reduce this. And then what's left over, I can plug the -5 into, right? So I get -5 squared is 25, -5 times -5 is 25, 25 plus 25 plus 25 is 75. But with L'Hopital's rule, we notice that it's 0 over 0, and so I say, oh look, I can just do the limit as x approaches -5 of the derivative of the top is 3x squared. The derivative of the bottom is 1. Now notice if I plug in -5, -5 squared is 25 times 3 is 75. Same answer, right? It's supposed to be the same answer. It's because this is one of the cases you could use it for. Anytime you have that indeterminate 0 over 0 form or infinity over infinity form. All right. Next, the limit as x goes to 0 of sine x over x. We saw this one and we proved it geometrically. It's kind of bad form in my opinion to use L'Hopital's rule for this, but we can. The reason why I think it's bad form is because we actually used this limit to prove the derivative of sine x. And I'm about to use the derivative of sine x to work L'Hopital's rule here. So it's kind of like circular logic, okay? However, to show you that L'Hopital's rule does also work here, the limit as x goes to 0 of sine x over x gives me 0 over 0 because sine of 0 is 0. Therefore, this can be shown to be equal to limit as x goes to 0 of derivative of sine x is cosine x, derivative of x is 1. And now if I plug in 0, cosine of 0 is 1, and I get 1 over 1 is 1. So of course we get the value we expect, right? It's defined that way. The main point of L'Hopital's rule, by the way, it's nice for things like this, but as you could see, I was already able to work it another way. But limits like, well, sort of like this one, we were able to do that one geometrically and squeeze theorem and things like that. But see the way these are mixtures. It's trig mixed with polynomial, transcendental mixed with non-transcendental, like normal, everyday functions. It's whenever you have mixtures like that, the limits get increasingly more difficult to work out normally. Here's another example right here. We graphed this function a couple of lectures ago with the curve sketching scheme that we were talking about. But one thing we didn't talk about was, I only mentioned it, that it had a horizontal asymptote as x went to infinity. In the last lecture, we talked about horizontal asymptotes and having limits as x goes to infinity, okay? But we didn't do anything like this because we didn't have any way of mixing the polynomial and the transcendental exponentials like that. But L'Hopital's rule gives us a very quick and clean way to negotiate these kinds of things. Notice, if I were to rewrite this limit like this, the limit as x goes to infinity of x squared minus 1 over e to the x. Because I'm using the negative exponent here to relocate the exponential in the denominator. And if I plug in let x go to infinity, I'll get an infinity over infinity type of indeterminate form. Perfect, right? Time to do L'Hopital's rule. So notice that would give me the limit as x goes to infinity. L'Hopital's rule means derivative of top, so that would be 2x over derivative of the bottom. Derivative of e to the x is e to the x. Notice I'm still getting infinity over infinity. Guess what? L'Hopital's rule can keep chugging until you get to either a form that's not usable, like 0 over infinity or something, or until you can figure out the answer. So infinity over infinity, I still have a limit that's indeterminate with infinity over infinity, so it still falls in the L'Hopital's rule category. Do it again. The limit as x goes to infinity, derivative of 2x is 2, derivative of e to the x is e to the x. Now, the limit as x goes to infinity of a number over e to the x, we got that limit last time in the last lecture. Remember, we have the large exponential in the denominator. The whole limit is going to go to 0. Okay? And if you remember, when we were graphing, y equals 0 is actually the horizontal asymptote of the function that we were graphing. Okay? So now you have another way of doing this. Real quick, I want you to notice how the differences between the two functions are really brought out with this property. The polynomials tend to go away, right? Because every time you do that derivative on a polynomial, you get lower powers and lower powers. But that exponential sticks around. That professes to the type of functions these are. Exponentials are always going to be more powerful functions than polynomials as far as size of the output goes. Exponentials are going to be way more increasingly increasing or decreasing, whichever one they happen to be. Okay, they're always going to be larger. So if you're doing these infinite limits like this, you can go ahead and just bank on the exponential one being the one that survives, right? And as you can see, that's true. Now down here, I wanted to demonstrate to you a couple of limits that don't fall under L'Hopital's rule. Notice if I plug in 4, it actually works out, right? If I do 4, I'll get 20 minus 7 is 13, and 8 plus 1 is 9. So that's the actual value of that limit. But notice if I were to do the derivatives, they're just linears, right? The derivatives would have given me 5 over 2, which is incorrect. Okay? This limit does not fall into L'Hopital's rule because I'm not getting a 0 over 0 or an infinity over infinity. Right here, limit as x goes to 0 of ln x over x. Now be careful here. This really needs to be a limit as x approaches 0 from the right because ln doesn't handle negative values. Okay? But in any case, notice what I'm getting here is negative infinity over 0. Because ln x from the right approaches a vertical asymptote as x goes to 0. And of course, x goes to 0. So look at it. Infinity over 0 is not one of our indeterminate forms. So this is not a limit that can be used with L'Hopital's rule. It must be one of those other indeterminate forms. So let's continue with more examples, but beyond that, these are going to be examples where they don't just start out ready for L'Hopital's rule. Instead, there are other indeterminate forms that you should recognize. By practicing, you'll start to recognize them, but you need to be able to recognize them when you see them as, hey, this could possibly work with L'Hopital's rule. In the last scene, I showed you a couple of them that right away you know they wouldn't work, right? If you didn't get the infinity over infinity, if you didn't get the 0 over 0, if you got infinity over 0, that's not going to work with it, right? But there are a few other indeterminate forms that are ones that will work with L'Hopital's rule, and you need to know what those are. Okay, so right here, 0 times infinity is one of those setups. In fact, in the last scene we did one of those. I just wanted to throw out the actual form here. So look, the limit as x goes to 0 from the right of x times ln x. This time notice what we're getting is a 0 times a negative infinity, because if you let ln of 0, it starts to go down to negative infinity there. So then how do we handle a 0 times infinity? Well, remember, we're interested in getting either 0 over 0 or infinity over infinity if we're going to use L'Hopital's rule. So in this case, it's easier for me to rearrange the x in such a way that I'm going to get an infinity over an infinity here. Okay? So watch, like this. I'm going to rewrite this as the limit as x goes to 0 from the right. And notice this is times x right here, right? Right? So that's also the same thing as divided by 1 over x. Now think about that for a second, right? If I divide by a fraction, I usually multiply by its reciprocal, right? So that's the same thing as times x over 1. So these are actually the same thing. Now, if you inspect, the ln will give a negative infinity, and 1 over 0 gives a positive infinity when it's from the right. So I've got a negative infinity over infinity right now, which is prime real estate for L'Hopital's rule. Okay, I have the infinity over infinity case right now, so I'm going to do my L'Hopital's rule, which is to take the derivative of just the top and just the bottom separately. Okay, so limit as x approaches 0 from the right. Derivative of ln x is 1 over x. Derivative of 1 over x is negative 1 over x squared. You can do that one with the power rule, right? That's x to the negative 1. Drop the negative 1 and get a negative 2 power. Now I can simplify this. This is the limit as x goes to 0 from the right of negative x squared over 1 times 1 over x, right? Division by the fraction, I just reciprocate and multiply. And so I'm left with the limit as x approaches 0 from the right of negative x, right? Because I can reduce the x's there, which now I can just plug in and see that that's 0. All right? So in this particular case, the 0 times the infinity gives me 0. And you're thinking, well, of course, anything times 0 is 0. That's not always the case. This isn't just an open and shut case of, hey, I see 0 times infinity, it's just always 0. That's not true. That's why you have to be able to evaluate these limits, because it matters what kind of infinities you're getting and what kind of zeros you're getting and what objects are bringing those in. Some objects are stronger than others. X being a polynomial tends to be a little bit stronger than a logarithm in certain cases. You just never know, and that's why we have limits that can do these things. Infinity minus infinity is another indeterminate form that we're interested in, and I know what you're thinking. Well, infinity minus infinity should be 0, right? Because it's just that simple. If you one big thing minus another big thing, they should just cancel out. No. Again, it matters what kind of infinities you have. There's all different kinds. Okay? I'm going to show you 2 different cases of infinity minus infinity and how they can actually be different values. They can be, they don't have to be. Okay? But the easier case, of course, would be, what if it was infinity plus infinity, right? That's obviously infinity as well. But when it's infinity minus infinity, you get that idea of, why don't we just, cancel these out? And there's that C word you want to avoid, okay? But again, it matters what kind of objects are bringing these infinities along and how do they compare to each other. Here I have an exponential minus a polynomial. Exponentials are notorious for being extremely powerful, especially when you're doing large numbers like infinity. So this is going to be a larger infinity pattern-wise than this infinity. They both go to infinity, of course. But I think you're going to find that since this one is that much stronger than that one, the big infinity minus the little infinity is still going to be a big infinity. Okay? Whereas down here with this one, this infinity and this infinity are kind of on the same scale, so you might actually get a number answer. Right? So let's take a look. With this one, I just remember that I'm over 1 like this. And then what I'm going to do is I'm going to divide both the top and the bottom by 2 to the x, like this. Okay? So then what I have here is the limit as x goes to infinity of 1 minus x squared over 2 to the x divided by 1 over 2 to the x. And using my limit laws, I can, sort of just look at each piece individually. But most importantly, this guy right here. Okay? If I do the limit as x goes to infinity of just this piece, that's going to give me an infinity over an infinity. Okay? So over on the side over here for just a moment, I'm going to work out that limit. In fact, we've already done a limit just like this in the last scene. But let's go ahead and write it out just for S and G, right? So it's infinity over infinity, so I can use L'Hopital's rule. That tells me, first step, that I get the limit as x goes to infinity of 2x over the ln of 2 times 2 to the x, right? Because the derivative of an exponential is itself, and since it's not base e, I have to put the little ln multiplication factor. It's still an infinity over an infinity, so I'll do one more L'Hopital's rule. X goes to infinity of 2 over ln of 2 squared times 2 to the x, like that. Okay? Now, from here, I can see that the answer to this limit is going to be 0. Because the only x variable is here in the bottom now, and the limit as x goes to infinity of something over infinity like that is going to be 0. Right? Okay. So what I have now is the limit of the 1 is 1, and the limit of this piece is 0. So I have this. The limit as x goes to infinity of 1 over 2 to the x, which of course I can renegotiate that back into the limit as x goes to infinity of just 2 to the x. And that's just a quick plug-in from some of the limits that we already know. It's an exponential function. X is going to infinity. The answer is infinity. Right? It increases without bound on that one. Okay? So sometimes L'Hopital's rule is helpful in smaller bits. Sometimes it helps with the whole limit. It just depends on where you need it. This guy right here is also an infinity minus infinity. Notice the x squared, of course, goes to infinity. X by itself goes to infinity. This one doesn't necessarily need L'Hopital's rule, though. It's deceptive on that one. Again, it's over 1, right? And what I'm going to do is I'm just going to multiply the conjugate. So I'm going to multiply both the top and the bottom by the square root of 5 plus x squared plus x. Like so. In which case, I'm going to get in the numerator, I'll have the limit as x goes to infinity still. But in the numerator, these two multiplied give me 5 plus x squared. This multiplication and this multiplication add out to 0. That's the whole point of doing the conjugate. And then negative x times positive x gives me minus x squared, which I hope you're seeing right away. X squared minus x squared is going to give me a 0. So I'm just left with 5 in the numerator. And my denominator is times 1, so it's 5 plus x squared plus x. So I have 5 over this is all I've got. Basically, now it's 5 over infinity, right? Because if I plug in the infinity, I've got infinity plus infinity. The denominator is definitely infinite, right? So it takes on this kind of format right here. I just have the limit as some, I'll let y represent this whole thing right here, like y, right? Go to infinity of 5 over y, right? Basically anything over infinity like this is going to 0. So here was my original point. You can have an infinity minus infinity in many different cases, and it does matter which things are bringing the infinities to the table. Infinity minus infinity in this case was still infinity because one of the functions was so much more powerful. Whereas this infinity minus infinity gave me an actual number, 0. Okay? So it does matter in all these indeterminate cases, the arrangement of the functions and the things that are bringing the infinities and the zeros. You have to be very careful and do your limits in an organized fashion to make sure that you're not missing anything. So let's finish up this lecture, this conversation, with 3 more examples from some other indeterminate forms. All of these have to do with exponents in some sort of way. So you'll find that we tend to use logarithms a lot. Should feel a little familiar, just like with logarithmic differentiation. Not quite as in-depth as that one, though. So let's start with 0 to the 0, right? Which is it? Is it 0 or is it 1, right? Anything to the 0 is 1, but anything times 0 is 0. So the limit is x goes to 0 of x to the x, right? So what we do with these methods is I start by letting my limit value equal something like L. So I just say, I know my limit's equal to something, so I'll just let it equal to L, right? From there, what I'm going to do is take a logarithm, an ln, of both sides of the equation. Using my limit laws, I can merge the ln into the limit so that it looks like this. The limit as x goes to 0 of the ln of x to the x is equal to the ln of my final answer L. But remember our logarithm rules, I could actually bring the x out right here, and I have the limit as x goes to 0 of x, put an arrow here, times ln of x equals to the ln of my L answer. Now, wait a minute. We just did this one, right? Limit as x goes to 0 of x times ln x, right? Where I flipped the x to being a 1 over x in the denominator, and that gave me a infinity over infinity, right? So L'Hopital's rule helped us do this limit right here, right? And we ended up with 0. We have 0 for this whole limit value, and we just did that one. So then from here, what this tells me is that 0 equals the ln of L. Therefore, I have to raise a base e on both sides, which is going to tell me that 1 is L. Anything to the 0 is 1. So I'm getting that the actual overall value of the limit as x goes to 0 of x to the x is 1. Same idea on these two limits. Notice how it's dealing with these exponents where I have variables both in the base and in the power. I'm going to be using that same method for both of these. Okay. Now, hopefully you recognize these as a lot of the limits that gets used with exponential growth and decay, and especially this one right here. gives us one of the results that we end up using a lot in algebra, and you never knew the limits that were behind it. Okay, so let's start with this one. Just like before, I'm going to let it equal something. It doesn't really matter what. So we'll just say something like D, right? Doesn't matter. And then just like before, I'm going to take a logarithm of both sides. So I'll do an ln here and an ln here. And then I can, of course, bring the ln into the limit. And remember, what that does is it allows me to drop the power out front. So here's where we're at. I've got the limit as x goes to 0 of x times the ln of 1 plus r over x equals to the ln of d. Don't let the r throw you off, by the way. R is just some number that gets used in some of those other situations. R is typically the rate, right? I'm just letting it be just some number. Just leave it there, okay? So now what do I have? I have 0 for my x, and then ln of 1 plus infinity, okay? So I have the ln of infinity is going to be infinity, and then I've got 0 times the infinity, right? So I can actually pull that same trick that we did in the last scene, where I do the limit as x goes to 0 of ln of 1 plus r over x over 1 over x, like so. And now look, I have r over 0, which is going to be infinity, right? And ln of infinity is still infinity. And then 1 over 0 is infinity. So I have infinity over infinity. This is now ready for L'Hopital's rule. I've just had to manipulate it a little bit, and I can perform L'Hopital's rule on this, which means I'm going to take the derivative of the top, which means I'll have 1 over 1 plus r over x, right? Derivative of a logarithm is 1 over the inside, times the derivative of the inside, which is going to be negative r over x squared, because the derivative of 1 is 0, and this is technically x to the negative 1, right? So I drop the negative 1, subtract, I get negative 2 power. So that's the chain rule for that one. And then, of course, the derivative of 1 over x squared gives me negative 1 over x squared is equal to the ln of value d. From here, notice the negatives will wipe out, and so will the x squares, right? So what I'm left with here, let me go ahead and split this. What I'm left with is the limit as x goes to 0 of r over 1 plus r over x is equal to the ln of d. Alrighty. So then if I were to multiply x in these three places, right, I could have the limit as x goes to 0 of x times r over x plus r is equal to the ln of d. And then I can let x go to 0. 0 times r is 0. 0 plus r is r. So I can actually do 0 divided by r. That's okay, right? I'm just getting 0 is equal to the ln of d. And then, of course, just like before, I raise a base e on both sides so that these will go away, and anything to the 0 is 1. So therefore, the value of this original limit as x goes to 0 of 1 plus r over x to the x is 1. All right? Now this one is the one that ends up getting used a lot with your exponential growth and decay. Let's finish up with that one. Again, pick just some value, right? I'll use m this time, right? And I'm going to take the ln of both sides just like we did before. So I'll have ln here, and ln here. And that will allow me, of course, to drop the x power out front. And let's see what that gives us. I have the limit as x goes to infinity of x times the ln of 1 plus r over x is equal to the ln of value m. So then what do I have here? I've got x going to infinity, so I have infinity. And then 1 over infinity is 0, plus 1 is 1, and the ln of 1 is 0. Well, that's infinity times 0. That's another one of those indeterminate forms that was workable, and I can just do the little flip trick again. If I do that same trick as I just did in the last example, limit as x goes to infinity of ln 1 plus r over x all over 1 over x, like so. Notice this is still 0 because I haven't changed it, and 1 over infinity right here gives me the 0. So I have 0 over 0. That's ready for L'Hopital's rule, right? And it's going to be the same derivative results as this one over here. Derivative of the top, derivative of the bottom. I end up with the limit as x goes to infinity of 1 over 1 plus r over x times negative r over x squared for the chain rule, divided by negative 1 over x squared from the derivative of 1 over x. And of course that's still equal to the ln of quantity m. The negatives won't survive, neither will the x squares, right? Because I can multiply those out. And I'm left with the limit as x goes to infinity of r times this. Right? So a lot of these steps should feel familiar from the very last problem we just did. But the ending is different. The ending is different here. Because watch. Now I have the limit as x goes to infinity of this. Right? R over infinity, it's just a number divided by infinity. That's going to go to 0. Right? We have that as one of our basic limits. Right? The limit as x goes to infinity of 1 over x was 0. We just talked about that one, right? So this piece right here is going to 0. And that just leaves me with r on that side this time. So I have r equals the ln of m. And then I can raise my base e on both sides. I have e to the r is equal to m. So there's my limit value right there. And that should seem familiar to you if you think back to some of your algebra days where you had p times 1 plus r over n to the nt power gave you the pe to the rt formula as you let things become continuous compounding, right? This is the actual limit that's used in order to switch from normal compounding to continuous compounding in algebra. Okay, so if you have one of the indeterminate forms that involves exponents, it's highly recommended that you throw an ln on both sides. Just let your limit value be some letter, and you know it's going to be equal to whatever that is eventually in the end. And then deal with your exponents this way, and hopefully it causes some sort of L'Hopital's rule that allows you to break it up more and interact the pieces. Okay? So I hope this has helped you understand L'Hopital's rule. Go practice that and do some limits. Next up, optimization.